Hi everyone. I'm thrilled to be a part of this event. Thanks so much for having me. My name is Nina McCurdy, and I am the Visualization and Public Outreach Coordinator for the very long name University of California High Performance Astro Computing Center. We call it UC HiPAC. A little bit shorter. Today I'll be showing 2 visualizations of simulations, and I'll also be giving a little background on cosmology. But before I do any of that, let me say a few brief words about HiPAC. We are a consortium of the 9 University of California campuses and the 3 Department of Energy laboratories. We began operating in January 2010. Our mission is to realize the full potential of the University of California's world-class resources in computational astronomy, and we do this a variety of ways. We offer small grant programs to fund collaboration within the consortium, and we also hold and host a range of HiPAC events. From our annual International Summer School on Astrocomputing to most recently a computational astronomy boot camp for science journalists. HiPAC is also committed to visualization and public outreach. Between our 12 research institutions, we have created so many beautiful visualizations of cosmology and galaxies smashing into each other and stars exploding. And not only are these visualizations gorgeous, but they also accurately depict the modern picture of the universe, the scientific picture of the universe. So at HiPAC, we really want to share both these visualizations, but also this picture of the universe with the general public. In the past few years, we've had 2 of our simulations featured in 2 different planetarium shows, one at the Adler Planetarium in Chicago and another at the California Academy of Sciences right here in San Francisco. We are also in the process of developing a 3D visualization lab at UC Santa Cruz, where HiPAC is based. And there we hope to develop and test our visualizations. And we're also about to go live with our HiPAC Visualization Gallery, where we hope to share and distribute these visualizations to both the science, the research community, and the general public. We are also part of the planning committee for the new exciting Science and Art Museum at UC Santa Cruz. Okay, now that you've heard my plug, I can move on to my main topic of the talk, visualizing simulations of cosmology and galaxy formation. And I'll start by talking about cosmology. In the past, the science of cosmology has suffered a lot of ridicule from astronomers for being full of theories and having very little data to back any of it up. However, in the past 2 decades, this has completely flipped, and a flood of new data has eliminated all but one theory. And that theory not only agrees with the data, but it predicts what we see in the data with increasing accuracy. The technical name is lambda CDM, or lambda cold dark matter theory. And we also call it the double dark theory. LCDM tells us that the visible matter in the universe, stars, dust, planets, gas, everything we can see with the greatest telescopes on or orbiting Earth, accounts for only 0.5% of what's actually out there. The remaining 99.5% is made up almost entirely of 2 invisible substances, dark energy and dark matter. So what are these substances? Well, let's start with dark energy. Fortunately, we don't know anything about dark energy.
Good.
It is the dominating ingredient in the universe, and until the late 90s, nobody even knew it existed. What we do know is this strange invisible substance is somehow causing the universe to expand at an accelerating rate. Dark energy seems to be perhaps a property of space itself that causes space to repel itself. So if you have more space, there's more repulsion and more expansion. But beyond that, we really don't know. We have a lot of work to do. Relatively speaking, we know quite a bit more about the other invisible substance, dark matter. So what is dark matter? Dark matter is elusive. It's invisible. It doesn't reflect or emit light the way that stars and gas do. And it doesn't absorb light the way that dust does. It also doesn't emit or reflect X-rays, radio waves, or any other forms of radiation. dark matter is non-interacting. It hardly interacts with anything, including itself, except it does interact with gravity. This is key. Under the force of gravity, dark matter particles collapse into dense blobs that we call halos, and it's within those halos that galaxies form. As it turns out, the galaxies that we are accustomed to seeing are all actually surrounded and permeated by these massive dense blobs of dark matter. These dark matter halos, bound by the force of gravity, keep these galaxies from flying apart in the expanding dark energy universe. So, understanding how and where these halos evolve is the key to understanding the evolution and the structure of the universe. And this has motivated scientists to run simulations to show this evolution, simulating the large-scale structure of the universe. So how do we cook up a universe like our own? Well, we start with a large number of non-interacting, invisible particles, dark matter particles, which in our case that number was 8 billion. And we spread these particles almost homogeneously throughout a specified volume. For us, that volume was a cube 1 billion light years across. What you're actually seeing here is just a portion of the entire volume. And we're not at the exact beginning of the simulation, but a little ways into it. But what I'm hoping you'll be able to make out is this grid-like structure. You see these lines, and it appears that what we've done is spread these particles out evenly and then gone in and jiggled them about a little bit. It looks a lot like the photon paintings.
Yeah, right.
We have these meticulously planned imprecisions that we're paying a lot of attention to because they'll determine the end result of our simulation. So what we're doing when we go in and make these meticulously planned imprecisions is we're trying to model the slight differences in density that were present in the universe right after the Big Bang. The theory of cosmic inflation tells us that these slight differences in density were caused by thermal fluctuations that occurred during a brief inflationary period right during the Big Bang. We actually have data that maps these differences in fluctuation, and we use that data to inform the way that we perturb and jiggle our particles. So once we have arranged our particles, we give each one an initial velocity, a speed and a direction. We press start, and we simply let gravity run its course. So what we're doing here is we're just stepping through a few different time steps of the Bolshoi simulation. And what you see as time evolves is these dark matter particles fall in and collapse to form these long filaments. And at the intersection of the filaments, you start to see these dark matter halos form.
Dark matter halo is a bright spot?
Yes. So we're only looking at dark matter right now. No gas, no stars, no anything. And the denser regions are bright, are the white spots. So this is great. It's beautiful. It's exciting. But how do we know our model is right? Well, we can compare it to observational data. So on the right, we have the distribution of galaxies that our Bolshoi simulation predicts. And on the left, we have the actual distribution of galaxies that are mapped out by the Sloan Digital Sky Survey. So it doesn't look like a perfect match, but when we compare it statistically, we find that we're predicting the distribution of dark matter halos with astounding accuracy. Just to give you an example, the Milky Way has two large satellite galaxies, the Small and Large Magellanic Clouds. The Bolshoi simulation actually predicts the likelihood of this. Wonderful. We're creating universes, toy universes, that behave a lot like we'd expect, a lot like our own. But what we really want to know is, how did our universe evolve? For this, we turn to constrained local universe simulations, or CLUES. So first we cooked up a universe like our own, and now how do we cook up our universe? We actually start with a very similar approach as before, but we begin by looking at observations of the structure of our local universe, and we try to figure out what the distribution of dark matter particles would shape that structure. So I don't have a little laser, but if we go to this image, we'll go and we see, okay, there's going to be a halo here and a halo here, and it looks like there's this filament, this thick filament here, and maybe some smaller filaments down here and around. So we can kind of get a sense of where the dark matter should live in order to create this structure. From there, we essentially run our simulation backwards to recover the initial conditions of our local universe. If only though it was that easy. This actually only recovers the largest scale structures. So from there, what we have to do in order to create a Milky Way or a Virgo-sized halo is we have to go in and add more little meticulously planned imprecisions in order to we have to experiment with that in order to create the Milky Way. So we do this experimentation over and over and over again. We add some smaller scale perturbations, run the simulation to present day, see what kind of structure is formed by that, do it again and again, until we finally come upon something that looks like our structure, that has a lot of similarities to our structure. And we do this at low resolution because it's very expensive on computers to run all these simulations. One high-res simulation takes something like 200,000 CPU hours on NASA's fastest computer. So we can't just be using all of our resources to make guesses and see what happens with them. So once we do have one that we like and we're happy with, we rerun those at very high resolutions. So this is what we came up with, and we're pretty happy about it. I don't know if you can make out, can everyone see pretty well? Okay. So yes, great. We have a Virgo cluster, a Coma cluster, the Great Attractor, a Perseus cluster. We don't quite have our local group yet. We're still working on a much larger scale. But from here, we can repeat this experiment to simulate an even smaller region that would include a Virgo cluster and a local group. And the Milky Way is part of the local group. So that's the level that we're at. That's the size scale. So now that you've sat through the background information, you get your reward. And perhaps it might be good to have the lights off for this video, if that's possible. The following visualization shows the evolution of the large-scale structure of the local universe. The first 30 seconds shows the evolution and is preceded by a minute of flying through the present-day local structure of the universe. This visualization is actually a low-res square version of the one that was featured at the Adler Planetarium in Chicago.
Musik zu hören. focus.
We're done. Okay. So in the last few minutes, I'll talk about galaxy formation. And since everyone's a little more familiar, I think, with galaxies, I won't provide nearly as much context, but I'd be more than happy to talk about the simulation aspect or the visualization aspect or in the open space afterwards. So the following movie shows a simulation of a pair of merging spiral galaxies as they would appear through a telescope, including star formation and star evolution and the absorption of starlight by interstellar dust. The colors approximate what would be perceived by a human eye. Regions containing young stars are bright blue, while dust absorption causes areas to appear darker and reddened. The duration of this simulated event is 3 billion years. So this is great because we will never be able to see anything like this in real life. Each galaxy is simulated with 1.7 million particles, and the simulation has been superimposed onto a field of distant galaxies to provide context. So we're only simulating one galaxy. We're not doing everything and focusing on this one. So as you can imagine, when I saw the OUBEY experience film, there's so many things that visually are similar to my work. I was completely blown away by it. Any questions?
Is there an awareness among your team that Pythagoras, this famous Greek mathematician and philosopher and mystic, always spoke, and I thought it immediately, that all the galaxies and all the stars have a sound. And I think there is research work done that, that in a certain perspective you can hear the sound of the earth, for example, or the sound of the sun. And that sort of comes into my mind, and I would say, yeah, I immediately believe that. But yeah, that's an age-old intuition. And yeah, is that sort of...
I don't talk about that, and we don't discuss it, but in my team. But the person that I'm actually here for, Dr. Joel Permack, he and his wife have written several books on popularizing cosmology, and I wouldn't be surprised if they do know a lot about that. And they're very in tune with that. But I would love to somehow integrate that into our visualizations, because I think that there should be music with these, and many people do include music. I didn't have it this time around because I want to find the perfect... So if anyone has recommendations, if you heard something, I was actually thinking your music would be really beautiful with some of these. Okay, we'll talk. That would be fabulous. Wonderful. So yeah, I'd like to know more about that.
So everything we saw there, those were suns, those were stars?
So they're not actually, we're not at that fine of a resolution. So every particle there is maybe like 500 solar masses or something. So every one particle actually represents 500 suns. So the more we can do it on a higher resolution, but that's not what we are looking at here. But people are doing it at incredible resolutions. So.
Every particle represents 500 suns, did you
Kind
say?
of, yeah. It's kind of, so, and actually, the one thing that I didn't want to overwhelm you with, but you actually see, so we're representing stellar evolution, so you actually see these particles fade from blue to red, and that's stars being formed, young stars that are then dying off in a period of 10 to 20 million years. So we're simulating that color, that change in apparent brightness of stars. So I'll just let this play while we're watching.
And this movement in levels, does it also have to do with the universe?
Do you just mean the camera movement?
Yeah,
No.
because you made first
A
the
dance.
spiral, and then the whole picture was
Oh. Yeah, so no, this is a very primitive form. We're actually, so the way that we create this is we take a simulation of galaxy formation and we send photons all around it, and then we do this ray tracing thing where we see how the photons would reflect off of the dust and the gas, and then they eventually come back and hit our camera. But I would love to put a track in there and have a camera that goes exactly the way I want to move it, but no. We're not doing any of that.
Just an association, it's for me like when these two sort of banged into each other and this light came out, it's like this, I mean, this is an age-old symbol for the spirit, this light.
Yeah. And actually, one of the main motivations behind this simulation is that when you have these massive mergers and these explosions that you're talking about, dust a lot of times will obscure most of the light. So when we look out and we see two galaxies merging, it will look like a very old galaxy because we're not getting nearly as much of the light. So simulating with dust allows us to really understand, oh, this is an incredibly energetic event that's going on right now.
And the colors in the film are related to the real colors, or
The
do you
color,
decide
yeah,
which
it's
color you take?
no. This is actually we're trying to well, when we see pictures from Hubble, we're putting our own colors in, right? But this is trying to recreate what we would perceive, how we would see if we were out in space, seeing this actually occurrence.
Yeah.
How large is the program that simulates this? So a lot of equations for each one of these? What makes
So-
the simulation run?
So we'll have an algorithm, and then I'm not actually sure how big the text files are that read in the data, but so with the dark matter simulations, we have our algorithm, but it's actually pretty straightforward. We tell how to move the particles, and then we only have the gravitational forces acting on each particle. So it takes a tremendous amount of computational time because we're calculating the force on every single particle and how that interacts. And with 8 billion particles, that's tremendous, but a lot of times we'll just save out the X and Y. We'll save out the location of the particles. That's all we'll save. So it's actually a pretty straightforward process. So.
I would say if you want, just go out, have a coffee, and you can go on with the discussion.